Hello, everyone. Welcome to our session. Today, we are going to explore a fascinating topic the importance of integral calculus and why it is essential in our professional field. I am Ana Sofia Hernandez, and today I am here with Gabriel Albarracin, a fellow biomedical engineering student.
Hi, Sophia. I'm very excited to be here and talk about calculus because it isn't just about numbers on a blackboard. It's a viral tool to saving lives and designing medical technology.
To get started, could just explain to use in simple words. What is integral calculus?
First, you must think of integration as the progress of accumulation. While the derivatives look at change at a specific moment, integrals help us find the total value, like the area under the curve or the volume of a complex object.
So it's like putting small pieces together to understand the whole picture.
Exactly. It's the mathematics of continuous growth and total sums.
That sounds powerful. Now, how do we apply this engineering? Can you mention some of the applications?
Of course, in signal processing, we use integrals to analyze signal from the heart, like an EKG, or of modeling physical phenomena, such as how heat or fluids move through a system. And another application that I can tell you is when we design a hip prosthesis. For example, we need to calculate the volume and the center of the mass of the implant to ensure it fits perfectly. We use integrals to determine how the material will deform under the patient's head. This ensures the implant won't fall after the surgery.
Okay, and specifically in biomedical engineering, why is it so relevant for our future career?
Because the human body is dynamic, we need integrals to calculate the dosage of a drug in the blood over the time, or to design prostheses by calculating the volume and the stress distribution in bones and other reasons.
Okay, now could you talk to use through one concrete, a real life example of how an integral is used in a hospital setting?
Yes, well, I think the perfect example is cardiac output, the volume of blood in heart pumps per minute. In a healthy adult is between 4 and 8 liters per minute. If it drops below 3.5, we are looking at cardiogenic shock. If it rises too high, it can indicate sepsis. It is one of the most critical parameters monitored in the ICU.
And how do you measure it? You cannot simply attach a flow meter to the heart.
Correctly. That's why clinicals use the Street-Wet Hamilton method. A known almost an indication substance, a dry or a cold saline, is injected into the right side of the heart, and a sensor in the aorta measures how its concentration changes over the time. The formula states that CO equals that almond divided by the integration of the concentration curve. The area under the curve tell us the total exposed of the sensor to the indicator, and from that we get the cardiac output.
So, can literally help a doctor diagnose a cardiac condition and monitor treatment in real time with an integral.
Yes, in modern ICUs, this is done automatically using a Swan GANS catheter as numerical integration method like Simpson's rule. Within seconds, the monitor displays the patient's cardiac output, but behind that number on the screen, there is always an integral running. And biomedical engineers are the ones who design, calibrate, and validate those systems. Integrals, calculus, it's not optional for us. It is the language in which medical technology is writing.
Oh, it's clear that calculus is the backbone of medical innovation. What is your final reflection on this?
Believe that as future biomedical engineer, magister integral calculus allows us to transform biological data into engineering solutions. It is the language of nature applied to technology.
Thank you so much for this explanation, and thank you all for watching. See you next time.